Hi, Math B. Today we are doing lesson 7.1a, an introduction to functions. And here's a little math joke for you. We're through. I need someone more functional. And the circle says, I thought you just wanted a well-rounded relationship. By the end of this lesson, you will understand this joke. So let's get started. Vanessa is buying bouncy balls at the arcade in Walmart, where for every quarter she puts into the arcade, she gets out 3 bouncy balls for every quarter. State the independent and dependent variables for the situation. So the independent variable here is the number of quarters. And this would be our x variable, and the dependent variable, the number of bouncy balls, depends on how many quarters that Vanessa puts in. So I'm just going to write the number sign, the number of bouncy balls. Complete the table of values and create a graph for this situation. Label each axis. Should the graph be discrete or continuous? Well, our x variable was the independent, and this was the number of quarters. And our y variable was the dependent, and this was the number of bouncy balls. So if we put 1 quarter in, we're going to get 3 bouncy balls. If we get 6 bouncy balls, we know we put exactly 2 quarters in. If we put 3 quarters in, we get 9 bouncy balls. If we got out 30 bouncy balls, then we can just backtrack and say we get 3 bouncy balls for every 1 quarter, so we would have to put 10 quarters in to get 30 bouncy balls. But I can't put a half of a quarter in and get out just 1 more bouncy ball. I put 1 quarter in 3, 2 for 6, 3 for 9, and so forth. So that means that this graph will be discrete. So the points will not be connected. So just to fill out this table real quick again, this is 1, 3, 2, 6, 3, 9, and 10, 30. So this is the number of quarters on the x-axis for my graph. And for the y-axis, this is the number of bouncy balls. So if I put 1 quarter in, I have 3. If I put 2 quarters in, I have 6. And if I put 3 quarters in, I have 9. And I can't graph if I put 10 and 30 in because it's off the graph. I do not connect this graph because it is discrete or not connected. Why is this situation graphed only in the first quadrant? Well, we can't have negative bouncy balls or a negative amount of money. We cannot have a negative number of quarters. So we couldn't actually graph in the second quadrant, and we couldn't have a negative number of bouncy balls either. If I were going to write an equation that represented this situation, I like to start my equations by just writing what I know. So I'm going to write that the number of bouncy balls is equal to 3 times the number of quarters. That means that my number of bouncy balls, I knew that was my y variable, so y equals 3 times my number of quarters was x. So there's my equation. This situation is an example of a function. In this situation, we would say that the number of bouncy balls purchased is a function of the number of quarters spent, or y is a function of x. A mapping is a representation of a relation and can also represent a function. A mapping is a diagram in which each input, these are our inputs, value is paired with exactly one output value. So for every x, we only have one y. The mapping to the right shows the relationship between the number of quarters spent and the number of bouncy balls purchased. Next problem, Kyle is across town at Bright Aid purchasing bouncy balls at their arcade. The table relates the number of quarters he puts into the machine and how many bouncy balls he gets out. Create a mapping and graph for this situation. So for the mapping, our mapping is going to be x and y. And again, we're going to have the number of quarters as x, so right here, and the number of bouncy balls for y. So for number of quarters, I have the number 1, I have the number 2, and I have the number 3. I'm getting that from here. Here, these are both 2, and this is 3. For number of bouncy balls, I have 2, 3, 4, and 6. 2, 3, 4, and 6. So for 1, if I put 1 quarter in, I get 2 bouncy balls. If I put 2 quarters in, though, I might get 3 bouncy balls. I might get 4. If I put 3 quarters in, I get 6 bouncy balls. So again, this x will be number of quarters, and this y will be number of bouncy balls. So for 1, I go up to 2. For 2, though, I can plot 3 and I can plot 4. For 3, I can plot 6. So this is asking, is this relation a function? And no, this is not a function, because for every input, or for every x, there is actually more than one output. If we put 2 quarters in, we could get 3 bouncy balls or 4 bouncy balls. So not a function. If we put 2 quarters in, we could get 3 or 4 bouncy balls. So this is not a function. It is important that you notice that it is not a function, because this part right here, if I have an x with an arrow pointing to 2 y's, it is not a function. If I have an x that I can plot 2 different y's, it is not a function. This next one says the cost of entry into a local amusement park is $45. Once inside, you can ride an unlimited number of rides. The mapping below represents this situation. Create a graph for the situation, label and number each axis. So if I'm going to graph this, we have the cost of entry for a local amusement park is $45. Once inside, you can ride an unlimited number of rides. So for our x, I should actually say that this is the number of rides, and our y is actually the cost. So if I were to actually draw this, we could see that it does not matter how many rides we ride. No matter what, let's just say that this up here is $45. No matter how many rides we ride, it's still going to be $45. So that means that we don't even have an x in our equation. This is a horizontal line, which is just y equals 45. And if I were to see, does this situation actually represent a function? I could say that yes, This is a function because for every input, there is only one output. So for every input, or x, there is only one output, or y. And I know this gets a little confusing because you're seeing a lot of arrows to the same y, but I'm only seeing one arrow from 0. I'm only seeing one arrow from 4. I'm only seeing one arrow from 8, and I'm only seeing one arrow from 10. If I could ride 0 rides and I could pay $45 or I could pay $60, then this would not be a function, but it's the same price no matter what. So a really easy way to tell if a graph is a function is by something called the vertical line test. So this is a visual way to determine if a curve is a graph of a function or not. A relation is a function if there are no vertical lines that intersect the graph at more than one point. So I could draw this green line right here, and it intersects the graph at this one point. This is a function right here. So the vertical line only intersects the graph at one point. If I'm going to look over here at this red line, this intersects this graph right here and right here. So this is not a function. The vertical line intersects the graph at more than one point. In this case, it intersects the graph at 2 different points. Directions. Determine if each relation or situation is a function. Explain your reasoning. Okay, so it is not mapping here and it's not a graph here. It just gives us some coordinate points. So for every input, there's only one output. That means for every x, there's only one y. So for 10, I have 2. For 3, I have -8. For 5, I have 2. And for 7, I have 1. So I do not have 5, 2, and 5, 3. That would not be a function. So I could say yes for every input, or for x value, there is only one y value, one output. For the next one, the amount of hours a person works and how much money they earn. So let's think about this. If I work, let's say I make $10 per 1 hour. So if I work 1 hour and I make $10, I'm not going to work 1 hour and then suddenly make $30. I'm going to work 1 hour and make $10. If I work 2 hours, I'm going to make $20. I'm not going to work 20 hours one day and make $50. If I work 2 hours, I'm going to make $20. So yes, this is also a function. A couple more examples. Determine if each relation or situation is a function. So for graphing, the easiest way to determine if something is a function is to use the vertical line test. And if I draw a vertical line on this graph, that only hits at one point. I could draw a vertical line anywhere on this graph and it would only hit at one point. So yes, this one is a function. If I come over here and look at this one, I'm going to draw a vertical line here. That only hits at one point. But if I draw a vertical line here, that hits here and here. So that hits more than one point. So this is not a function because this x, this point 1, I could have a y value here and a y value here when my x value is still 1. So now you should be able to get this joke. We're through. I need someone more functional. I thought you just wanted a well-rounded relationship. This graph on the left is calling this circle not functional because of the vertical line test, and this hits at more than 1 point. So hopefully this will help you with your 7.1a homework. Please join office hours and always email if you need some more help.